In this video, we're going to talk about Kirchhoffs Current Law, also known as KCL. Now, this is one of the first techniques you need to put in your tool bag as an electrical engineer. So what is Kirchhoffs Current Law? Kirchhoffs Current Law says the total current entering a node is going to be equal to the total current leaving a node. In other words, the algebraic sum of every current entering and leaving the node must equal 0. Now remember, Kirchhoff's current law is going to be one of the fundamental principles of electrical engineering that you need to remember and understand. So just remember, the total current entering a node must equal to the total current leaving a node. So this is Kirchhoff's current law in a nutshell. So always remember, the total current entering a node must equal to the total current leaving a node. Now let's look at this example. It says find I1. So they're going to give us this circuit diagram and they want us to find the current I1. So when we look at this circuit diagram, we know I1 is going to be in this branch. So we found I1, therefore our problem is complete. Haha, well, not quite, right? They want us to find the value of I1. Now, when we look at this particular circuit, they want us to use KCL to find this current I1. Now, we cannot use Ohm's law for this particular example. Why? Because we don't know the voltage or the resistance across this resistor. So the only other technique we know at this point in the course is going to be Kirchhoff's current law. So we're going to be using Kirchhoff's current law to solve for the missing currents. So the first thing you want to do anytime you're going to use Kirchhoff's current law is to identify the essential nodes. Now, what is an essential node? Well, we know an essential node is going to be a node that connects 3 or more elements. So for example, we know this point right here is going to be an essential node. Why? Because it connects this element, it connects this element, and it connects this element. Another way you can look at this is an essential node is going to connect 3 or more branches. So for example, it's going to connect this branch with this branch with this branch, right? Now, do we have any more essential nodes? Well, we know this is going to be an essential node right here. And this essential node connects this branch, and this branch. But this branch is in series with this branch. Therefore, this essential node is going to cover all of this because we know the current is going to be the same in this entire branch. Now, at the bottom here, we're also going to have an essential node. But the thing is, we're only going to have one essential node. I'm just going to label it right here. And this one essential node is going to be the node for all of the branches that come to the bottom wire. So when we look at this, we can see that this branch is going to come to this node. This branch also comes to this node, and this branch is going to come to this node. So because there aren't any resistors or source within these branches, this is going to form one big node. Okay, now that we've established that, the next thing I would like to do when identifying essential nodes is as soon as I identify an essential node, I like to label each node. So for example, I identify this as an essential node. So I'm just going to call this node 1. I'm going to call this node 2. And I'm going to call this node 3. Alright, so now we have to use KCL at one of these nodes to find the current I1. So because I see where I1 is, which is right here, I know I1 is going to be between node 1 and node 3. So I have two options. I can either take KCL at node 1 or KCL at node 3. For this particular example, I'm going to take KCL at node 3. So when I set this up now, I'm going to write KCL at node 3 Now when we start to solve for this, we know the current entering this node is going to equal to the current leaving this node. So let's find all of the current that is going to be entering node 3. When we look at this, we know the current I1 is coming into node 3, so we can write I1. Well, this current is leaving, so we're just going to leave that for now. But we also have this 6 milliamp current that's coming into node 3. So I'm going to say I1 plus 6 milliamps. But instead of writing milliamps, I'm going to write times 10 to the minus 3, which we know is going to represent milliamp. Now, we also have this 4 milliamp of current coming into node 3. So I'm going to have plus 4 times 10 to the minus 3, close bracket, equal. So now that we have covered the total current entering this node, let's look at the total current that's going to be leaving this node. Well, the only current that's going to be leaving node 3 is going to be this 20 milliamp. So I'm just going to write 20 times 10 to the minus 3. Okay, let's start to simplify this. So we're going to have I1 plus 10 times 10 to the minus 3 equals 20 times 10 to the minus 3. And when we start to simplify this, I1 is going to equal 20 times 10 to the minus 3 minus 10 times 10 to the minus 3. Now when you solve for this, I1 is going to equal 10 times 10 to the minus 3 amps. Therefore, we can write it as I1 equals 10 milliamps. So this is going to be our answer for the current in I1. So did you see what we did? We identified the current we wanted to find. We labeled all the essential nodes. Once we had the essential nodes, I just chose one of the nodes from the current I was trying to find. We could have chosen either 1 or 3. I decided to go with 3. I found the KCL at that node, and then once I found the KCL at that node, that gave me my answer, which is going to be I1 equals 10 milliamps. Alright, let's do another example. So this question says find I1. So where is I1? Well, we know I1 is going to be right here. So we don't know any of the voltages, and we don't know any value for the resistors. Therefore, we're going to have to use Kirchhoffs Current Law. The first thing we're going to do is just identify the essential nodes. This is going to be 1, and this is going to be 2. Now that we have identified our essential nodes, we're just going to use KCL. Now, for this particular problem, I'm just going to use KCL at node 1. If you prefer to use KCL at node 2, then go right ahead. It's really up to you on where you would like to perform KCL. So I'm just going to say KCL at node 1. So we should always remember what the definition of KCL is. So Kirchhoffs Current Law says the total current entering a node equals the total current leaving a node. So the total current entering node 1 is just going to be this current, which is going to be I1. So we have I1 equals the total current leaving this node is going to be 6 milliamps. So we can write this as 6 times 10 to the minus 3 plus we have the current in this branch, which is going to be 2 milliamps, 2 times 10 to the minus 3. And when we solve for this, we're going to get I1 equals 8 times 10 to the minus 3 amps, or you can just write it as I1 equals 8 milliamps. So this is going to be the answer for this problem. Okay, let's do one more example. Let's say we have this, right? They want us to find the current I1. So we know I1 is going to be the current in this branch here. And we're going to be using KCL to find this. Now the first thing we want to do is just label our essential nodes. We know this is going to be one essential node. This is 2. This is 3. This is 4. So we labeled 4 essential nodes for this problem. Okay. Now we know where I1 is. I1 is right here. Now for me, I like to be more methodical. So because I know I1 is the current we're trying to find, and I1 is between node 1 and node 3, I'm just going to do KCL at one of these nodes. So for this example, I'm just going to use node 1 to perform KCL. So I'm going to write this as KCL at node 1. We know the current entering this node is going to be 2 milliamps. So we can write this as 2 times 10 to the minus 3. And the current that's going to be leaving this node is going to equal, we have I1, so we can write current I1. But when we look at this, we know we also have this branch. Now in the original circuit, they did not label any current for this branch. But you should know that there is going to be a current in this branch. So anytime you're faced with a situation like this, you're going to have to label this current and choose the direction of this current. Now remember, you're just going to choose a random direction, right? I'm just going to choose a current for this branch, and I'm going to assume that this current is going to go away from node 1 in this direction, and I'm going to label it IA. Now this could be wrong, right? The current could actually be going towards node 1. Now the only way I can find that out is if I work through the problem. If I get a negative current for IA, that means the current actually is going to go in this direction here. But if I get a positive current for IA, then that means the direction I chose was actually correct. Alright, so let's continue, right? So we're writing a Kcl equation for node 1. We have the current leaving a node. We have I1. And we also are going to have the current IA leaving this node. So if I1 plus IA. Now when we look at this, we have an equation that has 2 unknowns. There is nothing we can do in this particular situation to find I1. Therefore, when you run into a problem like this, you're just going to now have to start finding KCL at other nodes. So remember, I want to find the current I1, which is going to be between node 1 and node 3. So because I already wrote the equation for node 1, I'm just going to now write the equation for node 3. So I'm going to say KCL at node 3. So this is going to be the total current entering a node equals the total current leaving a node. So I'm going to say the current I1 is going to enter this node. So we have I1 plus this current, which is 4 milliamp. I'm going to write 4 times 10 to the minus 3 equals the total current leaving this node. Now we don't have any current labeled in this branch. Therefore, I'm just going to draw in a current. And I'm going to draw this current to be IB. So the current that's going to be leaving this node is going to be IB. And when we look at this, once again, we have an equation with 2 unknowns. Now we cannot perform a system of equations where we use simultaneous equations to solve for these variables, because yes, we have I1, but then we have IA and IB. So now what we're going to have to do is, we're actually going to have to write a KCL equation at another node and see if that can help us. So let's write a KCL equation at node 2. So I'm just going to choose node 2. You can choose any node you like. I'm just going to choose node 2. I'm going to say KCL at node 2. The total current entering node 2 is going to be the current IA. So we have IA. Now let's see if any more current is entering node 2. We also have this 12 milliamp current that's going to be entering node 2. We have IA plus 12 times 10 to the minus 3. And we don't have any more current that's going to be entering node 2. So we're going to have equal. The total current leaving node 2 is going to be 4 milliamps, as you can see. So we have 4 times 10 to the minus 3. Now when you start to solve for this, IA is going to equal 4 times 10 to the minus 3 minus 12 times 10 to the minus 3. When you solve for this, IA is going to equal negative 8 times 10 to the minus 3 amps. IA equals negative 8 milliamps. Now the question wanted us to find I1, but this might be very important to us. So I'm just going to put a little box around it, right? This is not our answer, by the way. So we found the current IA, which is this current right here, and we know that's going to be negative 8 milliamps. So what that means is, in reality, this current is actually going to go this way. Now, once we have the current IA, I want us to look back up at the KCL for node 1. For the KCL at node 1, we actually found an equation that had a relationship for the current I1 and IA. Now that we know the value of IA, we can just substitute in the value of IA, which is negative 8 milliamps, into this KCL equation at node 1. So let's do that, right? 2 times 10 to the minus 3 equals I1 plus, we know IA is going to be negative 8 times 10 to the minus 3. Alright, so when you start to simplify this equation, we're going to have I1. Alright, so let's take this over to the next side. So we're going to have 2 times 10 to the minus 3 plus 8 times 10 to the minus 3 equals I1. Therefore, we can say I1 10 times 10 to the minus 3 amps, or you can write it as I1 equals 10 milliamps. So this is going to be our answer for this problem. I1 in this particular circuit is going to equal 10 milliamps. So this is how you solve any problem dealing with Kirchhoff's current law. In the other videos, we're going to talk more and do more examples with circuits dealing with Kirchhoff's current law.